Hello, my name is Gunnar Grün and I'm the Deputy Director of the Fraunhofer Institute for Building Physics, IBP, and Professor for Building Physics at the University of Stuttgart. I would like to welcome you to the submodule Energy Efficiency Enhancements of the module on the Lighthouse project in Lucknow. In this third video, out of 6, we will discuss energy efficiency enhancement possibilities for the Lighthouse project in Lucknow. Together, we will have a closer look at the energy balance equation. You will learn how to calculate the transmission heat sink. Moreover, we will have a look at the influence of moisture in building materials on the heat transmission. Based on this, we will have a closer look at how moisture affects the energy demand at the construction in Lucknow. Let's start by reviewing the energy balance basics from module 2.2 of the Lighthouse project in Lucknow. The balancing basics, as you can see them in this slide, were explained in the submodule. It was an explanation on both the equation as well as the graphical display you can see here. In this submodule, we will have a closer look at the transmission heat sinks. Here you can see the equation, which we used to calculate the transmission heat sink for a building. In total, it comprises of 2 main components: the influence of the heat transmission through the wall, calculated by the U value, and the influence of the heat bridges. But let us go through the equation step by step. With the equation, we calculate the heat loss in watt per Kelvin, temperature differences. It is calculated using the U value of each building component, multiplied with the respective surface. How we calculate the U values has already been explained in module 3.2. In addition to the U value, the heat loss from the heat bridges is also added. The value used is the sum of all heat bridges in the building, which will be explained in module 4.2 on the Lighthouse project in Indoor. This heat bridge value is multiplied with the total heat transferring enclosure area of the building. But now let's apply the formula right away. We will use the values from a flat in Lucknow, which you can see on this next slide. As there is just one wall type, we also have just one U value, which is 3.6 watts per square meter Kelvin. The area of the enclosure is 45 square meters, which in this case is also the total enclosure area. The heat bridge surcharge is set to 0.25 watt per square meter Kelvin, which is a typical value. With these values, we calculate the first part of the equation, and we get 162 watts per Kelvin. Using the heat bridge value and the total enclosure area, we can calculate the second part of the equation. The sum of these 2 results now gives a transmission heat loss for the apartment in Lucknow of 137.25 watts per Kelvin. Using this knowledge, you can now calculate the transmission heat sinks, also for all other construction types you might want to calculate. In the next part, we will now take a closer look at the influence of moisture on transmission heat loss. From different evaluations, we do know that the heat conductivity of a material is dependent on the moisture content of the material. As you can see in this graph, the influence is different according to the material that is used. but you can clearly see the trend. The higher the moisture content, the higher also the conductivity of the material will become. But let us have a closer look at one material, polystyrene. If we assume that we have a polystyrene material with a moisture content of 4%, we see in this diagram that the heat conductivity lays at 0.084 watts per meter and Kelvin. If the moisture content of the material is increased to 16%, this will result in a higher conductivity of 36% to 0.115 watts per meter and Kelvin. As the conductivity is directly linked to the U value, this increase in moisture will also increase the heat loss through transmission. Let us calculate an example for this. Let us have a look at the construction type in LUCKNOW. As mentioned before, the calculation of the U value is explained in module 3.2. So we will now use the values we have calculated back then. In this example, we use the same materials as introduced back then. But now we also increase the moisture of these materials according to the calculated moisture content resulting from the climate in LUCKNOW. For the lightweight concrete, which was calculated in dry state, we use the corresponding conductivity of 0.14. If this is increased to 20%, the conductivity is also increased to 0.22. The corresponding U values of 0.94 for the dry and 1.3 for the moist material is introduced in the table above. For the concrete, which was calculated also in the dry state, we used the corresponding conductivity of 1.7. If this is increased to 8%, the conductivity also is increased to 2.2. While the U value for the dry material is 3.6, this increases to 3.8 when wet, as you can see in the table here. Using these U values in the equation we have learned in this lecture, we can calculate the corresponding transmission heat sinks, which are also listed in the table above. We see that with higher moisture in the material, also the heat transmission is increased. Stating this, you may also ask about the overall influence on the energy demand for the flat we are looking at. We will now take a look at this influence. Let us start with a heavy construction in the dry state. Since there are both heating and cooling periods in LUCKNOW climate, the balance is presented divided into these two periods. For this construction, we have a heating energy demand of 43 kWh per square meter and a cooling energy demand of 72.5 kWh per square meter, which results in a total energy demand of 115.5 kWh per square meter. Since we have dealt with transmission heat sinks in this lecture, let us now take a look at what proportion of the total requirement these heat sinks take up. In the heating period, heat transmission sinks account for 27.9 kWh per square meter, which is almost 2/3 of the total demand. During cooling, this influence is even higher, so that the HT makes almost 90% of the total energy demand during cooling. A different picture can be drawn if we look at the light and dry construction. Firstly, the overall energy demand is reduced, as well as the influence of HT. This value is about 50% of the total energy demand in both cases. And if we now look again at what difference it makes when the material is moist, we see that the energy requirement increases slightly for both materials. Overall, it can be stated: the transmission heat loss depends on the moisture content of the material, and the lighter the construction material, the higher the influence of the moisture is. For this example, we also see that the formwork system with the light concrete filling has a total energy demand which is 22% lower than the one with the normal concrete filling. And with this, I would like to thank you for watching and to say goodbye.